Hello everyone. Have you ever been curious about how a spring damper system behaves? First, let us understand what a spring damper system is. A spring damper system is characterized by a spring which can provide a restoring force proportional to the displacement of the mass from its equilibrium position, and a damper which contributes to a damping force proportional to the velocity of the applied mass. This type of system can be found in your car suspension. It is also used to save lives as part of a building response to seismic activity. Commonly included in this system is a feedback loop such as a proportional integral derivative (PID) controller. It can provide stability to the system while allowing it to adapt to disturbance from external stimuli, thus allowing it to maintain the desired behavior. It also allows for a quick response time as well as tuning flexibility, leading to optimal performance based on specific requirements. The objective of performing this simulation is to elucidate the spring damper mass system behavior under the influence of a PID controller or without it. Besides that, it will allow for the identification of a system which can apply similar mechanisms as that of a feedback controller. The first step before creating the model in the software is to create a rough sketch of the system. This allows for a visualization of the model and thus quicker adjustments before using the simulation software. Next comes the setting up of the model in the simulation software. In this scenario, an open-source software known as A20MJ0098 is used to simulate this system. The components required are dragged from the side panel and placed in the workspace. Connecting each component can be done in the workspace as well. Shown here is a simple spring damper system. The spring and damping coefficients as well as the mass can be set before performing the simulation. It is now time to implement the PID system into the simulation. Simply add the components like before and set the initial parameters again before performing the simulation.
We're evaluating our model setup, which includes spring damper and force step components. These represent our mechanical system and the applied force. The setup allows us to simulate the system's dynamic behavior under the step input force. In our enhanced model setup, we've incorporated a sonar component, potentially a sensor providing real-time system data. This addition, interacting with other components, allows for closer system behavior monitoring. Despite the model's increased complexity, as evidenced by the additional libraries in the Libraries Browser panel, the Messages Browser panel confirms successful translation, indicating our model is correctly set up and simulation ready. In Task 3, we expanded our model to include a sonar component and ran a simulation. The graph generated from the simulation shows the system's behavior with and without the PID controller. The results visually demonstrate the effectiveness of the PID controller in stabilizing the system's behavior.
In the simulation of a simple spring damper system without a PID controller, it can be observed that the mass displacement will fluctuate and begin to reduce in amplitude before reaching a quasi-steady state at around 5 m. Notice that the behavior of the system represents a sinusoidal curve. Now, let's investigate the influence of the PID feedback loop on the system. Variations of the proportional term, integral term, and differential term values would lead to variations in the position of the mass right flange. Essentially, we can either reduce or prolong the time taken to reach the steady state by varying the parameters of the PID controller. Here, we can clearly see how the system fluctuates and reaches a steady state with and without the feedback control system. By varying the proportional term, integral term, and differential term values, we can obtain various steady-state time and force. After various parameters, it is found that a proportional term value of 100, an integral term value of 1 second, and a differential term value of 1 second exhibited the most favorable performance compared to all other sets. This concludes the presentation. We hope that you can better understand the chosen system as well as the way to simulate it in A20MJ0098. Thank you.